Hi everyone, my name is Peter Felfer and I'm from the University of Sydney. And in this video, I'd like to talk about how to extract interfacial access values from atom probe data. If you do atom probe analysis, you'll have situations like where you have a grain boundary or some other sort of interface, and there's more stuff there, or potentially even less stuff there of a certain species than somewhere else, and you want to know how much. Well, very often what you see people doing is using concentration profiles. Um, but actually, in atom probe tomography, especially at interfaces, concentrations don't really have a solid meaning because of aberrations. That's why we're using the integral number of atoms per unit area that are there in excess, called the interfacial access. And this is actually what quantifies the amount of segregation that you have, rather than the concentration. The way we do that, actually, it's been used in atom probe for quite a long time. So the paper that I'm showing you here is a paper from the Northwestern group, from David Seidman's group from the early 90s, where they've done interfacial access measurements on one-dimensional atom probe data. And essentially what you have is this a cumulative curve, which is the number of atoms of interest versus the number of all atoms. So if there's a constant concentration, it's a constant line. Then say you have an interface, you've got a higher concentration, it's not going to be a straight line, but you've got some other slope, and then you go into the other side of the interface, and there you have a constant concentration again, which might be different from the first one. And the difference at the interface between those two extrapolated lines, that's the interfacial access. And I'll give you a program that has an interactive user interface for that, so you can easily tweak and adjust so that you get the correct values and get the interfacial access of your data. Of course, this what the distance sorting is, so what the number of all atoms is versus distance. That's easy if you've got a one-dimensional case. We've got highly curved three-dimensional surfaces. So for this tutorial, we'll start out with a grain boundary here. It's actually fairly trivial. I've created it so that it's once again a reference data set. If you want to have it, just shoot me an email. It's unfortunately a bit too large to put it on my web page. And if you go through it, you have exactly 10 atoms per square nanometer. I know that because I've created it that way. And you would get pretty much exactly a curve like the one that you saw before. But then we will move on and do it for a highly curved surface, something like this. Actually, this very data, where we've got segregation to something that's that's fully three-dimensional, and you need some means to go along to measure the distance accurately of an atom to that surface. In order to do that, you can have a read through my paper that I've written about 2 years ago, and it came out last year, and it goes through how to do all of these things for interfacial access calculations and also mapping, which is a topic of a later tutorial for 0, 1, 2 dimensional objects in 3D atom probe data. And that's really the basis of that tutorial. Anyway, if you're interested in that, I'll throw the information about the relevant papers up on the web. And you can, of course, contact me if you've got more questions. So let's get cracking with the MATLAB part. So once again, we're going to do the analysis in MATLAB. We'll start with the grain boundary here that we've calculated the proximity histogram for earlier. And we'll just go and load the data in. So what we need, of course, is we need the POS file. So we need the parent POS file to get the cumulative number of all atoms. We need the so this is you have to go into the folder, of course, of all the programs that I've given you. And so we need the parent POS file, we need the interface, again, as a wavefront OBJ file. How to create that is a topic of a different tutorial. There's one up already for grain boundaries and things like that. And for more complicated shapes, you'll have to stay tuned. I'll still have to make one. Anyway, you go and add the the folders and subfolders to the path so we can load in data. And we'll simply go quick access value. And if we don't pass anything, it will just go and ask us for the information that we need. And I'll go into the folder with the grain boundary tutorial, load in the data file and the interface file, which is the waveform OBJ, and then the ranging file, xrange format. And with the second part, I'll show you how to do everything manually so that you have full flexibility in what you're doing. So if you've created an xrange file, again, you can get the xrange editor from my webpage. Then everything will be nicely laid out for you. So you'll get the tick box. We want to split up by atomic species. I've just called the one that's the excess species, I've just called it carbon. Click OK. You could also do it for all of the programs that I show you. You can also do it for the unranged values. So very often it's interesting to see a proximity histogram, for example, of all the unranged atoms, because it tells you, if you've missed out on a species somewhere. It can be very interesting as well. Anyway, now it does the sorting and all the math behind it, and it pops up with a graphical user interface that you can also save later. So since this is a very simple case here, everything by default is already very good, but usually you would need to change limits and the like, especially with the next data file you see. And to do that, you'll click on change limits. You click on where the current limit is. The closest one that you want is, of course, 4 limits, 2 for the lower. So 1 you can't see right now. So if I click here and move that just here, you can see the interpolation area for this curve, which is the approximation on the first side of the boundary for the concentration, happens between here and here, and the interpolation on the second side happens between here and here. So I can go and change those limits here as well. Of course, by default, they work quite okay. And the answer we're getting is that the interfacial axis is 9.99 atoms per square nanometer. I've created it to be 10, so I'd say that's pretty reasonable. And you'll see partial axis on one side and partial axis on the other side. So once you're happy with your approximations, you can save the figure. Usually you wouldn't necessarily put it into the paper, but in order to document the entire process, how you got the values that you would put in your paper, it's always a good thing to save it. So you go figure save. It either saves it out directly. In this case, I won't do it. I'll just press cancel, and it will pop up with a new MATLAB figure pre-populated with all of the things that we had in the interfacial axis graphical user interface. And you can, because you might want to, you might want to tweak the color of things, how, the thickness of lines. You might want to put some annotations in. Whatever you want to do. Very easy to do. And you can save it, and you'll have the information later. Anyway, I'll close that down, and we'll go to the trickier bits. So now I'm going to show you how to do everything in command line in MATLAB, and we'll do it now for the more complex situation here. We've got the segregation of nickel oxide to an interface. Again, this interface is a little bit more complicated to create, but don't worry, it's not super bad. It took me, I think, half an hour to create the whole thing. Anyway, so in order to do that, we'll go and load in the pos file, as in pos equals app, pos equals read pos, and that's some data I have from my colleague Barbara Scherer. So now we've got the pos variable in. If you click on it, you can see the 4 columns, X, Y, Z, and mass to charge. Very easy. The next thing we need is the interface, and we'll load it in as an OBJ. So you can go, I obviously remember which one I created. So I'll go in here. We've got the OBJ, and in the OBJ you'll see we've got vertices and we've got objects. So for our interface in an OBJ file, all the vertices belong to the entire file. Just to remember, let's see, vertices, OBJ vertices that are global. And we've got the objects, and in the objects, we've got only one object in this case, of course, and the object vertices are the triangles, which is a little bit confusing, but that's just, you've got to live with this. And now we've got our analysis object. So, and the last thing we need is actually the ranges, because we need to produce this, the POS file, or we need to extract just the nickel oxide, which is the species that we want to map, that we want to calculate the access for. And I'll show you how to do that entirely by hand. And for that, we need the RNG file, or RNG, it's up to you. We need Microsoft Excel or some other program similar to that. You can do it by hand as well, but this just makes it faster. And we'll get it in. So we'll need to get the ranges. I'll just, because I'll copy and paste, I'll just produce an empty variable called RNG for ranges and open it up so I can go and copy and paste later. And open Microsoft Excel, which I have open already. Produce a workbook, because that's what we're going to use to consolidate the formats. And go into here and find the RNG file and open it in the text editor. So if you go in here, you can see the ranges, and there's a lot of them because it's a very complicated system. But what we want are only the nickel oxide ranges. So you can see here, this is the single atom ones. So we'll find a nickel oxide down here, NiO. And if you look at it in the NiO column is here. So it's those 5 ranges. And I can go and mark those 5 ranges that I want to have. Of course, you know, you might have a less complex or a more complex situation, but anyway, you can just easily go into the RNG file or RNG file that you have produced using Arvis or whatever else means. You've produced your ranging file, and go Control Copy and paste it into Excel, and then go Data, Text to Columns. It's going to be fine this way already, and then we'll just copy those 2 columns out of there. I'll just do that in Excel. You can do that. You can delete the empty rows either here or in MATLAB. Doesn't really matter. Same story. Go Command Copy, and then right-click, paste Excel data. There we go. And our ranging. Now we've got the ranging information, and you've got the select ranges method here. So all I need to do is nickel oxide equals select ranges. Sorry, yeah, I had called them that one differently before. RNG, and we'll get our nickel oxide. It's about 66,000 atoms, so that's about right from what I remember. Let's just display it, so just to make sure that it's actually correct. So it's the scatter plot. It will get a little bit choppy. I'll get a little bit choppy for in MATLAB to display 66,000 points, but anyway, we can if we need to. And that's actually exactly what we wanted to see. So this is the nickel oxide at the boundary. You can see it's not super fast at rotating this amount of points. But anyway, we're just able to convince ourselves that it's actually the atomic positions that we want. So I'll just close that, and we'll call the access value calculation again. So I'll go quick access value of the POS file. So that's the parent POS file. The interface FV, and the nickel oxide. So the nickel oxide is what we're calculating the interfacial access for. And let's just launch that, and it will pop up with the graphical user interface again. One thing you'll see, of course, this is not artificial data, so the default values will need to be adjusted. But you saw that there's very clear interfacial access, and that's not a biggie then to adjust that. So here it's a little bit too close, and I suppose this is, now we're seeing a much better approximation of the lower limit, of the lower concentration, and this will probably need to go up to here roughly. But you can see here now the linear approximation on either side is actually pretty good now. We've got a reasonable interfacial access. It's not always that clear if you look, for example, in the paper that I've just shown you from the Northwestern group. At some of the boundaries, you'll see that the interfacial axis is much smaller, and that's actually not an unusual thing. That can happen very often. But of course, for tutorial purposes, I'm going to show you one where there is a reasonable amount of interfacial axis. Rule of thumb: if you can see the interfacial axis, you're probably going to have something like this. Maybe not as pronounced, but reasonable. That's pretty much all you need. So you click Figure Save again. I'll cancel that as well because I already have done that before. Maybe tweak it around a little bit. You can edit that number of cumulative number of excess species. We'll change that to nickel oxide. Up. Just to save it. That sort of edit you can easily make. Save it, and that's it. So yeah, you can go and download the code from a web page, and go and analyze your data with it. And if you're finding those things useful, I would encourage you to also cite the papers, my papers that are in the that I've put in with the as the information, because they are the relevant ones for that sort of analysis.